Meteorology is the interdisciplinary scientific study of the atmosphere. Studies in the field stretch back millennia, though significant progress in meteorology did not occur until the 18th century. The 19th century saw modest progress in the field after observing networks formed across several countries. It wasn't until after the development of the computer in the latter half of the 20th century that significant breakthroughs in weather forecasting were achieved. Meteorological phenomena are observable weather events that illuminate and are explained by the science of meteorology. Those events are bound by the variables of Earth's atmosphere, temperature, air pressure, water vapor, and the gradients and interactions of each variable, and how they change over time. Different spatial scales are studied to determine how systems on local, regional, and global levels impact weather in climatology. Meteorology, climatology, atmospheric physics, and atmospheric chemistry are subdisciplines of the atmospheric sciences. Meteorology and hydrology compose the interdisciplinary field of hydrometeorology. Interactions between Earth's atmosphere and the oceans are part of coupled ocean-atmosphere studies. Meteorology has application in many diverse fields such as the military, energy production, transport, agriculture and construction. The word meteorology is from Greek mu epsilon tau epsilon omega rho micron sigma meteorus, lofty, high, and lambda omicron gamma iota alpha logia, logi, i.e., the study of things in the air. History. The beginnings of meteorology can be traced back to ancient India, as the Upanishads contain serious discussion about the processes of cloud formation and rain and the seasonal cycles caused by the movement of Earth around the Sun. Varahamihira's classical work Brihadatsamhita, written about 500 AD, provides clear evidence that a deep knowledge of atmospheric processes existed even in those times. In 350 BC, Aristotle wrote Meteorology. Aristotle is considered the founder of meteorology. One of the most impressive achievements described in the Meteorology is the description of what is now known as the hydrologic cycle. The book De Mundo noted if the flashing body is set on fire and rushes violently to the earth, it is called a thunderbolt. If it be only half of fire, but violent also and massive, it is called a meteor. If it is entirely free from fire, it is called a smoking bolt. They are all called swooping bolts, because they swoop down upon the earth. Lightning is sometimes smoky, and is then called smoldering lightning. Sometimes it darts quickly along, and is then said to be vivid. At other times, it travels in crooked lines, and is called forked lightning. When it swoops down upon some object it is called swooping lightning. The Greek scientist Theophrastus compiled a book on weather forecasting, called the Book of Signs. The work of Theophrastus remained a dominant influence in the study of weather and in weather forecasting for nearly 2,000 years. In 25 AD, Pomponius Mela, a geographer for the Roman Empire, formalized the climatic zone system. According to Tawfiq Fard, around the 9th century, al-Dinawari wrote the Kitab al-Nabat, in which he deals with the application of meteorology to agriculture during the Muslim agricultural revolution. He describes the meteorological character of the sky, the planets and constellations, the sun and moon, the lunar phases indicating seasons and rain, the anwar, and atmospheric phenomena such as winds, thunder, lightning, snow, floods, valleys, rivers, lakes. Research of visual atmospheric phenomena. Ptolemy wrote on the atmospheric refraction of light in the context of astronomical observations. In 1021, Alhazen showed that atmospheric refraction is also responsible for twilight. He estimated that twilight begins when the sun is 19 degrees below the horizon, and also used a geometric determination based on this to estimate the maximum possible height of the Earth's atmosphere as 52,000 parseum. Saint Albert the Great was the first to propose that each drop of falling rain had the form of a small sphere, and that this form meant that the rainbow was produced by light interacting with each raindrop. Roger Bacon was the first to calculate the angular size of the rainbow. He stated that the rainbow summit cannot appear higher than 42 degrees above the horizon. In the late 13th century and early 14th century, Kamal al-Din al-Farisi and Theodoric of Freiburg were the first to give the correct explanations for the primary rainbow phenomenon. Theodoric went further and also explained the secondary rainbow. In 1716, Edmund Halley suggested that aurora are caused by magnetic effluvia moving along the Earth's magnetic field lines. Instruments and classification scales. In 1441, King Sejong's son, Prince Munjong, invented the first standardized rain gauge. These were sent throughout the Joseon dynasty of Korea as an official tool to assess land taxes based upon a farmer's potential harvest. In 1450, Leon Battista Alberti developed a swinging plate anemometer, and was known as the first anemometer. In 1607, Galileo Galilei constructed a thermoscope. In 1611, Johannes Kepler wrote the first scientific treatise on snow crystals. Strenna seu nive sex angula. In 1643, Evangelista Torricelli invented the mercury barometer. In 1662, Sir Christopher Wren invented the mechanical, self-emptying, tipping bucket rain gauge. In 1714, Gabriel Fahrenheit created a reliable scale for measuring temperature with a mercury-type thermometer. In 1742, Anders Celsius, a Swedish astronomer, proposed the centigrade temperature scale, the predecessor of the current Celsius scale. In 1783, the first hair hygrometer was demonstrated by Horace Benedict de Saussure. In 1802–1803, Luke Howard wrote on the modification of clouds, in which he assigns cloud types Latin names. In 1806, Francis Beaufort introduced his system for classifying wind speeds. Near the end of the 19th century, the first cloud atlases were published, including the International Cloud Atlas, which has remained in print ever since. The April 1960 launch of the first successful weather satellite, TIROS-1, marked the beginning of the age where weather information became available globally. Atmospheric composition research. In 1648, Blaise Pascal rediscovered that atmospheric pressure decreases with height, and deduced that there is a vacuum above the atmosphere. In 1738, Daniel Bernoulli published Hydrodynamics, initiating the kinetic theory of gases and established the basic laws for the theory of gases. In 1761, Joseph Black discovered that ice absorbs heat without changing its temperature when melting. In 1772, Black's student Daniel Rutherford discovered nitrogen, which he called phlogisticated air, and together they developed the phlogiston theory. In 1777, Antoine Lavoisier discovered oxygen and developed an explanation for combustion. In 1783, in Lavoisier's essay, Réflexions sur la phlogistique, he deprecates the phlogiston theory and proposes a caloric theory. In 1804, Sir John Leslie observed that a matte black surface radiates heat more effectively than a polished surface, suggesting the importance of black-body radiation. In 1808, John Dalton defended caloric theory in A New System of Chemistry and described how it combines with matter, especially gases. He proposed that the heat capacity of gases varies inversely with atomic weight. In 1824, Sadi Carnot analyzed the efficiency of steam engines using caloric theory. He developed the notion of a reversible process and, in postulating that no such thing exists in nature, laid the foundation for the second law of thermodynamics. Research into cyclones and airflow. In 1494, Christopher Columbus experienced a tropical cyclone, which led to the first written European account of a hurricane. In 1735, an ideal explanation of global circulation through study of the trade winds was written by George Hadley. In 1743, when Benjamin Franklin was prevented from seeing a lunar eclipse by a hurricane, He decided that cyclones move in a contrary manner to the winds at their periphery. Understanding the kinematics of how exactly the rotation of the Earth affects airflow was partial at first. Gaspard Gustave Coriolis published a paper in 1835 on the energy yield of machines with rotating parts, such as water wheels. In 1856, William Ferrel proposed the existence of a circulation cell in the mid-latitudes, with air being deflected by the Coriolis force to create the prevailing westerly winds. Late in the 19th century, the full extent of the large-scale interaction of pressure gradient force and deflecting force that in the end causes air masses to move along isobars was understood. By 1912, this deflecting force was named the Coriolis effect. Just after World War I, a group of meteorologists in Norway led by Wilhelm Bjerknes developed the Norwegian cyclone model that explains the generation, intensification and ultimate decay of mid-latitude cyclones, introducing the idea of fronts, that is, sharply defined boundaries between air masses. The group included Carl Gustaf Rossby, Tor Bergeron and Jacob Bjerknes. Observation networks and weather forecasting. In 1654, Ferdinando II de' Medici established the first weather-observing network that consisted of meteorological stations in Florence, Cutigliano, Vallombrosa, Bologna, Parma, Milan, Innsbruck, Osnabrück, Paris and Warsaw. Collected data were centrally sent to Florence at regular time intervals. In 1832, an electromagnetic telegraph was created by Baron Schilling. The arrival of the electrical telegraph in 1837 afforded, for the first time, a practical method for quickly gathering surface weather observations from a wide area. This data could be used to produce maps of the state of the atmosphere for a region near the Earth's surface and to study how these states evolved through time. To make frequent weather forecasts based on these data required a reliable network of observations. But it was not until 1849 that the Smithsonian Institution began to establish an observation network across the United States under the leadership of Joseph Henry. Similar observation networks were established in Europe at this time. In 1854, the United Kingdom government appointed Robert Fitzroy to the new Office of Meteorological Status to the Board of Trade with the role of gathering weather observations at sea. Fitzroy's office became the United Kingdom Meteorological Office in 1854, the first national meteorological service in the world. The first daily weather forecasts made by Fitzroy's office were published in the Times newspaper in 1860. The following year a system was introduced of hoisting storm warning cones at principal ports when a gale was expected. Over the next 50 years many countries established national meteorological services. The India Meteorological Department was established following tropical cyclone and monsoon-related famines in the previous decades. The Finnish Meteorological Central Office was formed from part of Magnetic Observatory of Helsinki University. Japan's Tokyo Meteorological Observatory, the forerunner of the Japan Meteorological Agency, began constructing surface weather maps in 1883. The United States Weather Bureau was established under the United States Department of Agriculture. The Australian Bureau of Meteorology was established by a Meteorology Act to unify existing state meteorological services. Numerical weather prediction. In 1904, Norwegian scientist Wilhelm Bjerknes first argued in his paper Weather Forecasting as a Problem in Mechanics and Physics that it should be possible to forecast weather from calculations based upon natural laws. It was not until later in the 20th century that advances in the understanding of atmospheric physics led to the foundation of modern numerical weather prediction. In 1922, Lewis Fry Richardson published Weather Prediction by Numerical Process. After finding notes and derivations he worked on as an ambulance driver in World War I. He described how small terms in the prognostic fluid dynamics equations that govern atmospheric flow could be neglected. and a finite differencing scheme in time and space could be devised that would support numerical prediction solutions. Richardson envisioned a large auditorium of thousands of people performing the calculations and passing them to others. However, the sheer number of calculations required was too large to complete without using computers, and the size of the grid and time steps led to unrealistic results in deepening systems. Through numerical analysis later found that this was due to numerical instability. Starting in the 1950s, numerical forecasts with computers became feasible. The first weather forecasts derived this way used barotropic models, and could successfully predict the large-scale movement of mid-latitude Rossby waves, that is, the pattern of atmospheric lows and highs. In 1959, the UK Meteorological Office received its first computer, a Ferranti Mercury. In the 1960s, the chaotic nature of the atmosphere was first observed and mathematically described by Edward Lorenz, founding the field of chaos theory. These advances have led to the current use of ensemble forecasting in most major forecasting centers. To take into account uncertainty arising from the chaotic nature of the atmosphere, climate models have been developed that feature a resolution comparable to older weather prediction models. These climate models are used to investigate long-term climate shifts, such as what effects might be caused by human emission of greenhouse gases. Meteorologists. Meteorologists are scientists who study meteorology. The American Meteorological Society published and continually updates an authoritative electronic meteorology glossary. Meteorologists work in government agencies, private consulting and research services, industrial enterprises, utilities, radio and television stations, and in education. In the United States, meteorologists held about 9,400 jobs in 2009. Meteorologists are best known by the public for weather forecasting. Some radio and television weather forecasters are professional meteorologists, while others are reporters with no formal meteorological training. Equipment. Each science has its own unique sets of laboratory equipment. In the atmosphere, there are many things or qualities of the atmosphere that can be measured. Rain, which can be observed or seen anywhere and any time, was one of the first atmospheric qualities measured historically. Also, two other accurately measured qualities are wind and humidity. Neither of these can be seen but can be felt. The devices to measure these three sprang up in the mid-15th century and were respectively the rain gauge, the anemometer, and the hygrometer. Many attempts had been made prior to the 15th century to construct adequate equipment to measure the many atmospheric variables. Many were faulty in some way or were simply not reliable. Even Aristotle noted this in some of his work, as the difficulty to measure the air. Sets of surface measurements are important data to meteorologists. They give a snapshot of a variety of weather conditions at one single location and are usually at a weather station, a ship or a weather buoy. The measurements taken at a weather station can include any number of atmospheric observables. Usually, temperature, pressure, wind measurements, and humidity are the variables that are measured by a thermometer, barometer, anemometer, and hygrometer, respectively. Professional stations may also include air quality sensors, ceilometer, falling precipitation sensor, flood sensor, lightning sensor, microphone, pyranometer, peer heliometer, spectroradiometer, rain gauge, snow gauge, scintillation counter, seismometer, transmissometer, and a GPS clock for data logging. Upper air data are of crucial importance for weather forecasting. The most widely used technique is launches of radiosondes. Supplementing the radiosondes, a network of aircraft collection is organized by the World Meteorological Organization. Remote sensing, as used in meteorology, is the concept of collecting data from remote weather events and subsequently producing weather information. The common types of remote sensing are radar, lidar, and satellites. Each collects data about the atmosphere from a remote location and, usually, stores the data where the instrument is located. Radar and lidar are not passive because both use EM radiation to illuminate a specific portion of the atmosphere. Weather satellites along with more general-purpose Earth-observing satellites circling the Earth at various altitudes have become an indispensable tool for studying a wide range of phenomena from forest fires to El Niño.